Hi, and welcome to 5.5H Inclined Plane with Friction. Students will be able to create a free body diagram for an object on an inclined plane with friction this time, and students will be able to calculate the frictional force and analyze the motion of an object on an inclined plane. So I figured we'd get right into it. We kind of already have all the tools we need in our toolbox, but now we're just applying them to some pretty fun situations, and that's fun with a PH for physics fun. Number one says a 10-kilogram wood block is released from rest on a wood ramp that is inclined 30 degrees above the horizontal. Does the block remain at rest or slide down the ramp? So it's just hanging out there in the beginning, and then you release it, but does it slide down or does it remain on the incline? If it does slide down the ramp, what is the block's acceleration? And if it doesn't, what is the minimum angle that would make the block slide down the ramp? You could increase the steepness of this ramp. And then what is the tipping point for the block to start sliding down? Pretty interesting question. If you want, you could pause it and set up your own free body diagram and try to do an analysis. Let's get right into it. So I'm going to draw my free body diagram, and it's going to look like this. We have our block on the incline. Okay, it's 30 degrees. Yep. All right, and then you ask yourself, what forces are acting on the block? Is there gravity? Yes, there's gravity. So we make Fg. Is this thing on a surface? Yes, it's on a surface. So there is a normal force. Okay, and is there friction? Yes, there's friction. Now, what direction is the friction going? We know it's parallel to the surface, all right? The frictional force always resists the motion of where this thing wants to go. And you might already know in your head, this block wants to go down the ramp, so friction will act against that motion. So we'll call that F. And is this static or kinetic? Well, it starts at rest. So right now it's static, and we want to know, is the component of the weight that acts parallel to the hill, this component here, Fg parallel, is this greater than the maximum static friction? If this one's greater, it's going to slide down the hill. If the maximum static friction is greater than the parallel component of the weight, the maximum static friction will maintain the equilibrium and the block will stay on the hill. If it does stay on the hill, then if we increase this angle, what ends up happening is this increases and the perpendicular component of the weight decreases. This should be perpendicular. Okay, so this will get smaller, but this gets bigger as this increases. Anyway, that's the setup for this problem. I'll write down the given. So the mass is 10 kilograms. G is negative 9.8 meters per second squared. And they even tell you it's wood on wood. So we look at the diagram. Wood on wood is over here. The static coefficient is 0.42. We might need that kinetic coefficient for the next part if it starts sliding down the ramp, right? But right now it's at rest. If it starts sliding down the ramp, then it's going to switch to kinetic. Don't forget that. So let's start our analysis by looking at the perpendicular direction. We'll do the net force. We'll add those two forces together. So the net force in the perpendicular direction is equal to the normal force minus Fg perpendicular. In this direction, it's not accelerating. Those forces balance each other out, so the net force is 0. We're looking for the normal force. And spoiler alert, the reason it's important for the normal force is because we're going to use it for our frictional force later. So that's kind of why we're starting with this one. Minus, now Fg perpendicular. Okay, remember this one? This angle is the same as this angle, so this is 30 degrees. And now you have your right triangle. Fg perpendicular, is that opposite, adjacent, or hypotenuse? That's adjacent. Now we'll be able to determine Fg because we know the mass. Is Fg the opposite, adjacent, or hypotenuse. This is the hypotenuse. So adjacent and hypotenuse. Are we going to use sine, cosine, or tangent? We're going to use cosine. So the shortcut is you take the vector FG and you multiply by the cosine of the angle. That's just a quick review. We're going to be doing a lot of the shortcut for all of these problems in this lesson, so hopefully you're comfortable with that. Now remember, FG is just equal to mg, so we can break this down even further. Mg cosine theta. So the normal force is equal to the mass, 10 kilograms, times 9.8 times the cosine of the angle, which is 30 degrees. And when you do that multiplication, you get 84.87 newtons. So we know this is about 85 newtons. Cool, that's good. Now we should be able to figure out the frictional force, and we should be able to figure out FG parallel. And basically, if the frictional force, you could do it separately. If the frictional force is bigger than this one, then it stays still. And if you want to do it separately, that's fine. But I'm going to draw my net force equation in the parallel direction. All right. Now, what forces are acting in the parallel direction? We have just this one and this one. So we have the force of friction static minus FG parallel. So we don't know what the net force is doing yet. We don't know if this thing is going to start moving. So this is still kind of unknown. So we could leave it as the net force parallel, just like that. The force of friction is equal to mu Fn. The mu static, it's static friction. And Fg parallel is equal to, well, similarly, Fg parallel is opposite the angle here. Okay, so opposite and hypotenuse. That's going to be sine. So you take the vector that we're breaking into components, Fg, and you multiply it by the sine of the angle. Okay, we could break this even further. So the net force, oh man, my hand is really like getting in the way of things here. The net force is equal to mu, and then Fn we said was, well, if we wanted to, we can still have it be, we said the normal force was equal to mg cosine theta, so you could rewrite it mg cosine theta, just so you see the relationship here. Now Fg is equal to mg, so this turns into mg sine theta. This is the parallel component of the weight. This was the perpendicular component of the weight, which was equal to the normal force. All right, don't be intimidated by all these letters here, okay? Hopefully you could work through it and see that where all these letters are coming from. All right, now you can plug in what we know. We still don't know what the net force is doing, but we know the coefficient is 0.42 because we're looking at the static. We're seeing how much force does it take to actually start moving, overcome this frictional force. The mass is still 10. We're still on Earth. The cosine of 30. Am I going to run out of room? I don't know. Well, we already knew what this number was. So if I wanted to, I could rewrite it like this. This is still just our normal force, which we solved for already. And then this becomes 10 minus 10 times 9.8 times the sine of 30 degrees. All right, so this portion, this term is the frictional force. And this term over here is the parallel component of the weight. And before I said, okay, we're really just comparing these two and seeing which one is bigger, which one is going to win. So we're almost there. Let's figure it out. We're still not sure what the net force actually is. But we know that the frictional force is equal to 35.65 newtons, and the parallel component of the weight is equal to 49 newtons. Oh, so this one is 49, and this one is only 35.65. So the net force is actually in the negative direction, which we defined as the down the hill, kind of to the left, in the direction of the parallel component of the weight. The net force is equal to negative 13.35 newtons. And then it starts sliding down the ramp because FG parallel is greater than the maximum static friction. So the parallel component of the weight's enough to overcome that. I said that multiple times already. Hopefully you get it. Now, if it does, part B, if it does slide down the ramp, what is the block's acceleration? So now this thing is moving, okay? Gravity didn't change. So those components are still the same. The angle is still the same. The normal force didn't change. But what did change was the frictional force. It is no longer static friction. So this is going to become kinetic. We don't know what this kinetic friction is yet, but we can figure it out. And then once we know what the kinetic friction is, we could determine what the new net force is going to be. It's no longer this, because this number was for the static friction. So let's redo this. So now some things are changing because we are sliding down the ramp. So this is now the kinetic friction. And what else is changing? We know what's happening in the net force type of situation. It's starting to slide down the ramp. It is accelerating because the parallel component of the weight is larger than the frictional force. Oh, but Mr. Nangle, you didn't solve for the frictional force yet. How do you know that this is larger? Well, we solved for the static friction, and even the maximum static friction was less than the parallel component of the weight. And if you remember, the kinetic friction is always less than the maximum static friction. So therefore, we know this parallel component of the weight is going to be larger than the kinetic friction. And if they're unbalanced, then we know it's accelerating. And if it's accelerating, we know the net force is equal to ma. So that's where that comes from. The force of friction kinetic is now mu k Fn. The normal force stays the same, luckily. And Fg parallel stays the same. It's still just Fg sine theta. Everything else is pretty much the same except this coefficient, and now we know more about the net force and we could actually calculate the acceleration. So the mass, so you can start plugging in some numbers here. Are we ready to do that? Well, might as well rewrite it the full way. So mu k Fn minus mg sine theta. And now we know all of those different variables. We could plug them right in. The mass is 10. We are looking for the acceleration. The kinetic coefficient for wood on wood is 0.30. The normal force is still 84.87 because we didn't change the angle of the ramp. The mass again is 10. This is negative 9.8, but really we'll just call it 9.8 because we're already taking into account the direction in our net force equation and the sine of 30 degrees. If you're able to follow with me with the, I know I was going kind of fast there with my explanation, but then if you're able to follow that, you kind of have a good grasp of what's going on. Now we just have one equation and one unknown, so you could solve for the acceleration and you get 2.35 meters per second squared, and it's going to be in the negative direction because that's the direction that the parallel component of the weight is, and this number is bigger than this number. All right. This is actually, oh, did I solve for it? No, but you could solve for it if you want. Cool. All right, next problem. Example 2. A 20 kilogram steel block is released from rest on a steel ramp that is inclined 15 degrees above the horizontal. Does the block remain at rest or slide down the ramp? And if it does slide down the ramp, what is the block's acceleration? And if it doesn't slide down the ramp, what is the minimum angle that would make the block slide down the ramp? Tricky one. I wonder if it's going to be like a part C situation now where the maximum static friction is greater than the parallel component of the weight, and we need to increase this angle until we figure out when the maximum static friction is equal to the parallel component of the weight. Okay, so if you want, with that little hint, you could try it on your own first and see where you get. Let's start by drawing our free body diagram, just like we did before. Okay, so we have our weight, there's gravity, the block is on a surface, so there's a normal force. There is friction, so the friction acts up the hill, opposes the motion, and we can even break this into the perpendicular and parallel components. Then we'll draw in our units, so we don't get points off for units, because that's always a pain. And we have to look up, okay, steel on steel, so that looks like it's over here. Right now we're stationary, so we'll use 0.74. If the block starts moving and we need to calculate the acceleration, then we'll use the sliding, the kinetic friction, to calculate that. So we know the coefficient of static friction and the kinetic. The first thing that we're going to do is write our net force equation in the x direction, or in the perpendicular direction, I should say, in the almost like the y direction. So it's like this, okay? Then we know that the net force is equal to 0, and the normal force is what we're looking for. And just like before, FG perpendicular is FG cosine 15 degrees, because that's adjacent, and FG is the hypotenuse. So the shortcut method for the perpendicular component is FG cosine theta. All right. That turns into mg because FG is equal to mg. And then you could plug in some numbers. So the normal force is minus 20 times 9.8 times cosine 15. And that gives you a normal force of 189.3 newtons. So we know this is 189.3 newtons now. That'll help us determine what the frictional force is when we do the net force in the parallel direction. So the net force in the parallel direction is the frictional force minus the parallel component of the weight. Again, we don't know what's happening in the net net force, side of things. So we have to leave this as the net force because we're not sure yet. But we could calculate both of these things and get numbers for each one. So the frictional force is equal to the coefficient of friction times the normal force, and this is our shortcut again. This time for parallel, FG sine theta because it's opposite the angle. Okay. We could, break this down even further by saying that the normal force is mg cosine theta, which we proved basically over here. We didn't actually write that equation down, but we could have. And fg sine theta turns into mg sine theta. So just breaking it out before we add in all these numbers. So the coefficient of static friction is 0.74. This is the mass times the acceleration due to gravity. It's a 15-degree angle. And just like before, we could have plugged in 189.3 over there if we wanted to. Okay. So then the frictional force becomes 140 newtons. This is all for the frictional force. The parallel component of the weight is 50.7 newtons. So this is all the work for the parallel component of the weight. The minus sign means they're working against each other. So which one is winning? This time, the maximum static friction is larger than the parallel component of the weight. So this frictional force, and you could kind of see in the diagram the way I drew this, the frictional force is greater than, or at least it's shown to be greater than the parallel component of the weight. In reality, these are just in equilibrium, and the frictional force is equal to 50.7 newtons. All right, because that is what is exactly balancing out the parallel component of the weight, which we calculated is 50.7 newtons, right? So this can increase up until 140 newtons. And how would we increase this frictional force? And how would we increase this parallel component of the weight? Is by increasing the angle. The steeper this angle is, the longer this component of the weight will be, and the shorter this component of the weight will be. Up until, let's say you make it a 90-degree angle, okay? All of this, if this was our box now, the weight would be acting straight this way, which is parallel to our surface, which is now 90 degrees. It's like a wall. So it would drop straight down, right? So at 90 degrees, that's the maximum size that this could be. Really, you would just use you wouldn't break it into components anymore because it's acting straight down, but that's just showing that the larger the angle is, the larger this component of the weight will be. And we'll find a breaking point, a tipping point, where we want this to be equal to the maximum static friction. So that's where we're going to go next. All right, hopefully that makes sense. All right, so, and then I also said that when you do this subtraction, you get a positive number, and we made the positive direction up the hill because we made the frictional force positive. This is positive, and this was negative. So since we got a positive number, the math tells us even that it doesn't slide down the ramp because, yeah, for the reasons I explained. So the way we want to solve for this is by saying, okay, the frictional force, the maximum static frictional force, let's make that exactly equal to the parallel component of the weight. At which angle, will make this parallel component equal to that maximum static friction? When they're equal to each other, then what does that tell us about the net force? If these two quantities are equal to each other, the net force is equal to 0. So let's start writing our equation. It looks the same so far, but the thing that's different is our goal is to find out when these two forces are equal to each other. And like I said, if they're equal to each other, the net force is 0, and that's going to be the main difference for how we're handling this now. Because before we were saying, well, which force is winning? And what happens? Now we're saying, okay, we want the net force to be 0 because that'll tell us the point where any angle greater, this will start winning. So that tells us the exact angle where these two are equal to each other, and then any angle greater than that angle is when it starts sliding down. This overcomes the maximum static friction. So that's the reason we're setting this equal to 0. It's important to realize what we're doing and why. Once we have this set up like this, we just plug in what we know. So the frictional force is equal to mu Fn, and the parallel component of the weight, the shortcut, is Fg sine theta. We could break this down even further by remembering that the normal force is equal to the perpendicular component of the weight, which is mg cosine theta. And we have that over here. And this Fg is equal to mg. So now we have two trig functions here in the same equation. Interesting. Well, let's clean this up a little bit. Let's swing this to the other side by adding it to both sides of the equation. And now we have an mg term on both sides, so those cancel out. Right? Just divide both sides by mg. Then we can, the whole point, what are we trying to do? We're trying to solve for the angle. So we want to try to get the isolate the variable still, basically, right? So let's try to combine like terms by dividing both sides by cosine theta. All right, so if we divide both sides by cosine theta, then we have sine theta over cosine theta. Now remember, the goal is to try to isolate this variable. So how can we rewrite sine divided by cosine to try to do that, to try to isolate the variable? This is where a fancy trig function comes into play. So you have to remember that sine divided by cosine is equal to tangent. That's kind of like the definition of tangent, is that it's sine divided by cosine. So that's a fancy move right there. All right. Once you know, once you like this, you might have gotten stuck here. It's like, what's the heck? What do I do next? Yeah, it's a trig identity. So you had to like really do some trig, I guess, to get the theta. It's not too bad of a trig identity, but it is something that you might have gotten stuck on. Okay. Now at this point, remember your goal is to isolate the variable. So how do we solve for theta? Do you remember? We've done it before in this class. All you have to do is take the inverse tangent of both sides. Really what you're doing is tan -1. All right. And just like if you have 5x is equal to 10, how do you solve for x? Well, this is 5 times x. So I do the inverse of times. And I'm doing the inverse of tangent. And the 5's cancel out and the tangents cancel out. But whatever you do to one side, you have to do to the other. So I did an inverse tangent on this side. I have to do the inverse tangent on this side. It all comes back to we're just isolating the variable. So that's kind of what's happening there. And then now, believe it or not, this is the equation that tells you, it all boils down to that equation. That'll tell you what the angle is. So you just plug in the coefficient of static friction for whatever scenario you're talking about, and boom, that tells you what the angle is going to be. So it really gets simplified down, but it really does, you have to do all this work to prove that's why. So it would be a 36.5-degree angle. Anything slightly more than this, and then the parallel component of the weight is going to be greater than the maximum static friction. Good stuff. Now this one's just kind of a fun challenge one. It says block A is 5 kilograms and is on a 10-degree inclined plane, is tethered by a string to block B, which is 20 kilograms, and on a 30-degree inclined plane as shown in the diagram below. The coefficient of friction between the blocks and the surface is 0.1. Which block slides down the ramp? What is the acceleration of the system? And what is the tension in the string? We're already 27 minutes into this lesson, and it's like I said in the beginning, this is more of like an application of what we already know. So if you're not up for the challenge, or if you want to pause the video and watch this at a later point, that's totally fine. At this point, you can do the worksheet that's associated with this lesson. So I know I'm going to go over time on this, but I think it's a good question. So like I said, if you want to pause, do the worksheet, and come back to this for a little challenge at a later date, that's totally fine. But I'm just going to keep it in this lesson because it kind of goes along with what we've been doing. So this will be a long video. Anyway, number 1 says which block slides down the ramp. So this B is 20 kilograms, and it's on a pretty steep incline. Block A is only 5 kilograms. All right, so which one so far is winning? Block B is winning because it's heavier. But, oh, maybe the incline has something to do with it too. Well, this is only a 10-degree incline. So since this is a steeper incline as well, we know it has every reason to be going in this direction. So it's going to be pointing in that direction there. So we will make, as I do this problem, this is the positive direction. So it's going to accelerate that way. Any force that points this way is going to be negative, and any force that points this way is going to be positive. Same with this. This is negative, this is positive. So let's do some physics. Let's start by drawing a free body diagram for block A. Now remember, we said that it's accelerating, this block is accelerating up the hill. So you have to draw that in. It'll help you remember what direction is positive. Now, is there gravity acting on the block? Yes, there's gravity. Is the block on a surface? Yes, so there's a normal force acting perpendicular to that surface. Then I ask myself, okay, is there a rope involved? Yes, there's tension pulling you up the hill that way. And then is there friction? Yes, there's friction, and the friction acts opposite the motion. So it's pointing that way. Now you can see, I alluded to this earlier in a previous lesson, but if we look at our axes this way, we can see that this is the only one that's out of alignment, which is why we always break the weight into components, because we want them to be on these set of axes. If we tried to use just the traditional horizontal X and Y axis, then yeah, the weight would be on that axis, but then we'd have to break the frictional force up into components, the normal force into components, the tension into components, and that is just a lot of work. So instead, we'll break the weight into two components, and now we have these that are acting along our axes, and that'll be the end of breaking things into components. So that's good. Now we are going to make the net force in the perpendicular direction. That is just these two forces here. So we have the normal force minus the perpendicular component of the weight. The net force in that direction is 0. We're looking for a term for the normal force, and this is the shortcut, Fg cosine theta. Fg is equal to mg, and now we have an equation for the normal force, mg cosine theta. The parallel direction, we have a net force equation that looks like this. The tension is the only thing in the positive direction. The weight, the parallel component of the weight, is acting down the hill, and the frictional force is acting down the hill as well. So those are both minus. All right. Now we know that the object is accelerating, so the net force is equal to ma. The tension is what we're looking for. This is the shortcut for mg, Fg parallel. And this is the frictional formula, mu Fn. So we'll break this further. Fg is equal to mg. The normal force is equal to mg cosine theta. So I'm just plugging in what I know. And then we could plug in numbers. And you get an equation that looks like this. Now we're not done, but this is important to know. This will help us determine part A, the acceleration, and then part B, the tension. So that's for block A. So we'll keep that on the side over here. On block B is accelerating this way. It's heavier, right? Gravity acts on it more than on block A. So it's accelerating down the hill this way. So again, is gravity acting on the block? Yes. Is there a normal force? Yes, it's on the surface. Is there tension in a rope? Yep, this way it's pulling that way. And then what direction is friction acting? The real question is, what direction is this thing moving or trying to move? It's moving down the hill, so friction acts up the hill. You could have two forces that point in the same direction like this. That's fine. I like to separate them out so I could see them separately. Yeah. Then we'll break up the weight into its perpendicular and parallel components. And we're ready to write some net force equations. In the perpendicular direction, it looks very similar to what we had before. And in the parallel direction, it also looks pretty similar. We have the parallel component of the weight acting in the positive direction, and the frictional force is in the negative direction, and so is the tension in the rope. That's also in the negative direction. All right, we know this thing is accelerating, so Newton's second law says the net force is equal to ma. This is the shortcut for the Fg parallel, Fg sine theta. Frictional force is equal to mu Fn, and we don't know what that tension force is. We could break it out further. Fg is equal to mg. The normal force is equal to mg cosine theta. And then you plug in what you know. And you solve. And now we have two equations and two unknowns. We have 20a is equal to 81 minus ft. And we have 5a is equal to ft minus 13.3. Two equations, two unknowns. That's enough to solve for both. So 2 equations, 2 unknowns, and there's actually 2 different ways that we can solve. The quick and easy way to do it is to actually add these 2 equations together. To do so, we'll rearrange that second equation there so that everything's in line, and you could just straight up add them together like that. So 5a plus 20a is 25a. These forces cancel each other out, and then you have negative 13.3 plus 81 is 67.7. If you're not comfortable with that way, or if you don't believe me, you could do it a different way. Oh, and then the acceleration, you could actually solve for it now. It says 2.7 meters per second squared. So if you wanted to do it a different way, you could take one equation, solve for a variable. So in this case, I added 13.3 to both sides, and I said that the tension is equal to 5a plus 13.3. Then you take your second equation and you plug in for the tension. There's our 5a plus 13.3. Then it's just a matter of combining like terms. All right. Well, first I distributed the negative. Then you combine like terms. So you add 5a to both sides and you get 25a. And then you add, oh, and then you do 81 minus 13.3 and you get 67.7. And then you just divide, and it's the same answer, 2.7 meters per second squared. You don't have to do it this way. I'm just showing you that this adding the equation thing works, in case you haven't done that in a while or have never seen that. So now we're almost there. We have one of the variables, and all we have to do is just plug it back into one of our original equations. So here's one of our original equations. Plug in 2.7, and we have a tension of 26.84. The real test is going to be if we plug A into this equation, do we still get the same tension? And we do. So that's a good indicator that we did our work correctly. Or did we? What's wrong with this picture here? I forgot to write my units in the very beginning, even though, oh, Mr. Nangle, I wrote them in my final answer. I know, the New York State Regents wants you to write the units for the given information, even though they told you it in the problem and it's on the page that they gave you, they want you to write them down on your response. So that's the rules, I guess. Yeah, I don't know. Not great. If you do all of this work correctly, you're going to get a point off if you don't write for those. It's frustrating. But so is long videos like this. So why don't I just end it already? That's about it. Thanks for watching and have a great day.